voltage drop. So for the next few minutes, I'm going to just talk about mostly, nothing much physical, but more about circuits, right? So I have a resistor here. If I define, so you define current going this way, right? Then there's a voltage drop here. And delta P is given by I times R. Okay? And the voltage is higher upstream, lower downstream. Okay? Current this way, high voltage. This is low voltage. Okay? And so we did a few examples of circuits last week, not last week, on Monday. We show equivalent resistance, whatnot, for resistor in series, parallel. This is called a resistor, by the way. You can do the same thing for a voltage drop for a capacitor. If I have a capacitor here, C, okay, and the voltage drop across from point A and point B, delta AB is given by Q. Okay, so if this is plus Q and this is minus Q, then the voltage on A, V at A is higher. Okay. So let's do an example.
Isn't it?
So, by the way, you can do the same thing with capacitor in series, capacitor in parallel. I don't know if you guys have done this before. So briefly, right? Briefly, capacitor. I don't think this is universal somehow. Two capacitors in parallel, C1 and C2, and you connect it to a demon battery of potential V, right? Then we ask what's the equivalent capacitors, right? The equivalent capacitance still by this diagram is equivalent. Okay, so you do the same thing here. You do the Kirchhoff's law, right? In this case here, it's actually much simpler. I don't have to worry so much about current here. There is no resistors. And if I go through this loop, right, then the voltage drop across these 2 points, right, say going that way, right, is equal to Q over C1, let's call this C1, C2, okay, minus, going across the demon, you have the minus sign, minus V is equal to 0, right, and then the other one is a Q over C2, if I go across the other loop, right, this is loop 2, this is loop 1, minus B equal to 0, right, so what do I have here? In this case here, then B is equal to Q over C1, B is equal to Q over C2, and here B is equal to Q over C equivalent, right? What am I trying to do here? Did I make a mistake somewhere? Somehow I cannot think. I don't have it on my note here somehow. So what I was trying to show is that C equivalent in this case here is equal to C1 plus C2. I think I got lost in the answer here.
That's right. How do you know that Q is the same for?
Yes, you're right. The potential is the same, right? Q is not necessarily the same.
I think one way to define that might be to say, like, if you take the derivative of Q with respect to time, you get like current.
Current, yes.
You
But this
say
is
like current equals capacitance times change voltage, and then like
right.
your current laws do that.
Now I know what to do that. I know what mistake I made. But you don't have to consider that you're really static, right? You turn on the battery and immediately it reaches steady state.
Yeah.
Right. But I understand your point, right? So what happened? If we charge in Manu, we solved it, right? This is great. So what happened here? Q1. So here you have Q1, here you have Q2, right? So this is Q1 and Q2. Okay. So from the first part of the Kirchhoff law, right? Then Q has to be equal to Q1 plus Q2. Right? The total charge on plus Q minus Q, just because of the conservation of current. Right? Current going in has to be equal to current coming out. Right? So if I have current coming out I here, right? It has to split into two, I1 and I2. Therefore Q has to be equal to Q1 plus Q2. Right? But Q1 is equal to C1 times V, Q2 is equal to C2 times V. You sum them, Q1 plus Q2 is equal to C1 plus C2 V, right? And then this is equal to Q, right? This is equal to Q, which is equal to C equivalent times V, right? Equal to C1 plus C2. If we cancel, the equivalent capacitance becomes C1 plus C2. Okay? Questions so far? Okay. And then if you attempt the same kind of thing, if I have two capacitors, C1, C2 here, connect it to a demon, the voltage source, and the V, you will find the C equivalent, doing the same kind of analysis, which I will not go through. I think when I'm doing this, this becomes 1 over C equivalent is equal to 1 over C1 plus 1 over C2. This is what you will find. Okay, the formula is the reverse of the formula for the resistors, right? For the resistors, when you have a resistance in series, they add, right? And when you have a resistance in parallel, then they have this kind of formula. And this is the capacitance in series. This is in parallel. Okay. Question? Now, let's do an example where we have a circuit with both the capacitor and the resistor. So we're looking at the discharge of a capacitor. So say initially you have plus Q here, minus Q here. Okay? So So what happened is that because they're connected by a resistor, then current will flow, okay? And I define current to be positive going that way, okay? So I has to be equal to Q dot, right? Minus Q dot, sorry. Because in this case, if I goes up, Q has to go down, okay? Current is a movement of positive charge, mathematically in this case, right? So if I increases that way, then the plus Q will drop. Okay. So let's do the Kirchhoff law on this, right? The voltage drop across here, okay, is what? Is I times R, okay? And then I go in the other direction, right? Here the voltage drop is actually going opposite from minus Q to plus Q. So I actually have a minus sign, minus Q over C. That has to be equal to 0 for the second Kirchhoff law. Okay? But I is Q dot, right? So minus Q dot R minus Q over C is equal to 0, right? So Q dot is become minus 1 over RC times Q. Right? This is the differential equation, right? And
what is Q dot?
Q dot is the minus dq dt.
Oh.
Okay? Anytime I put a dot, it's a time derivative. You familiar with this? Or
Yeah.
You just forgot, right? So the solution of this is that Q as a function of time is equal to Q naught. So initially you have Q naught here, minus Q naught, times e to the minus T over RC. Okay? And the voltage across the voltage across the capacitor, and so different. P as a function of time. P is just Q over C, right? Then this becomes just P naught e to the minus T over RC, right? Where P naught is Q naught C. Okay? And same thing here, you can find the current. Current is a function of time. Current is a time derivative of Q with a minus sign, right? Minus dq dt. And when you do that, you'll find that this is equal to V naught over R, C cancel. I'm skipping some math here. Minus T over RC. Okay. As the capacitor discharge is plus Q move across the circuit to neutralize the capacitor, right? The charges go down exponentially. The voltage drop across the capacitor also goes down exponentially, and the current eventually dies off exponentially, right? And there's time constant. They all have this curve like that. Okay? And this time here, tau, is the time constant for an exponential. The time to reach 1 over e of the initial value, right? This RC, this is called the RC time constant. I don't know if you guys deal with circuit a lot, but if you study electronics, this is mentioned about RC time constant. Anytime you have a circuit, anytime you have a capacitor, and then you have a resistor, then there's an RC time constant for it, right? And this discovering how current drops and how voltage drops.
Wait, how do you get from that equation to E to the power?
here, this equation.
Yeah.
How do I get this?
Yeah.
Yeah, this is just a solution. Anytime I have dx dt equal to some minus alpha x, okay, then the solution becomes x as a function of time. This equation of e to the minus alpha. You can just, one way to solve it is just plug this into this equation, and you get the equality. Right? Okay. So, is this clear, this step, that step here, right? This is just dq dt. Right? dq dt is minus 1 over rc times q, right? And anytime you see a differential equation like that, then you know that that variable falls as an exponential. Okay. Question so far?
So do you like integrate both sides, or what do you have to both sides?
Do I integrate both? Yes. What's the best way to solve this? That should be easy. I mean, go through a math over yes. Separate the variable.
Yeah. So you dq on one side, dt on the other.
Right. Yes. Yes. Right.
This
Yes.
is what you did.
What's happening to my thing here? Right. So if I have dx dt is equal to minus alpha x, then this is dx over x is equal to minus alpha t, right? And then you integrate.
Oh, okay.
Right? And then you have log of x is equal to minus alpha. Okay? And then you have that equation. Right? Okay. Question?
For this graph,
Yes,
is the arrow pointing to the line or like the?
I'm pointing this is the, so if this is a 1, then this becomes 1 over e. So tau is the time it takes when the value of the current or the voltage of the charge has dropped to 1 over e of its original value, right? That's called the 1 over e time constant, right? And that happens when the time is equal to RC, right? If this time is equal to RC, right, then this becomes 1 over e, right?
Okay.
If I just say take one of these equations, let's take these equations, okay? And if I have v equal to v naught e to the minus t over rc, right? If t is equal to rc, then this becomes e to the minus 1. Right? So the voltage has dropped to 1 over e of its original value. Right? And that's called the 1 over e time constant. Right? And in this case, for the case of electronics, it's called the RC time constant.
And so just the equation of that line is the whole
The equation of this line.
of the curvy one. I don't know.
No, I'm just, so this is an exponential curve, right? This is, say, this t as a function of time.
Okay.
Okay. And then I'm just saying that this is tau. Okay, and tau is RC. Okay. So this is actually quite a general property. I know we've been talking about circuit, but let's go back to our physics discussion. In particular, as usual, we'll talk about the parallel plates. Okay. In parallel plates, and if I have a resistive material in between, right, a resistor in between, so this is in our discussion when I have a solution of ions, right? Which actually I might do, I don't remember that, right? The capacitor of a parallel plate is given by epsilon naught A over S, right? Where A is the area, S is this is separation, okay? And the resistance across this material, right? The resistance R is given by, I don't know if you remember the formula, it is basically this is rho times rho is the resistivity, right, times S over A. Right? And then remember that the larger the area, the smaller the resistance. The longer the material is, the larger the resistance. Right? So here in this case, you'll see that tau, the RC time constant, here then becomes just rho S over A times epsilon naught A over S. Right? So the A cancel, the S cancel. Right? And then what you're left with is epsilon naught rho. Okay, this is the RC time constant. So as you realize, this is independent of size and shape. Okay. So meaning that because capacitance actually increases with area and drops with the separation, but resistance actually is the other way around. The product of the two is independent of area and separation. Right? So the geometry drops, you're left with only physical variable, epsilon naught and rho. Right? And this is a general property of material. So if I have anything of any shape, right? If you remember your discussion of conductor, right? Things of any shape can have a certain capacitance, right? It has also a certain resistivity, right? And the product of the two is always constant.
So would that time constant be like measuring the what if you like polarize it and then it went back to neutral?
Yes, correct. Yeah. So if you polarize a media, right, and then how long does it take for everything to become neutral again, right? And that is given by this equation. And this is the limit. It doesn't matter. You think, well, if I want to make the time constant longer, right, maybe I can make the size much bigger, right? Then it can hold more charges, right? Then maybe things will last a lot longer. But that's not true. If I increase the size, the capacitance increases, yes, but the resistance drops proportionally. The product is constant. This is actually important, say, in a lot of circuit design, say in particular, right, your liquid crystal display. I don't know if you know this. This is inside. I believe they use this, right? The liquid crystal is this polymer material that is aligned like that. When you apply voltage, right, if you close a circuit, you apply voltage drop here, then what happens is all these molecules suddenly align itself like this. Right? The molecule is polar, applying a voltage, everything suddenly turns, right? And then this is how, and one mode of the polarization gives you transmission, and the other mode gives you electric light. Right? So in this case here, it's like this, then maybe light can transmit, a polarized light can transmit. But the molecule is like that, then it actually absorbs all the polarized light. Right? And this is how you get. I don't know if this is still like that in iPhone, but in the past, your old monitor, before it becomes an LED monitor, right, a liquid crystal monitor, liquid crystal display, it was a DIMM. That's how it operates, right? Like blocking and unblocking light. Right? And what happened here, this is a capacitor, right? But this material is a resistive material, right? So if you don't do anything, right, the voltage will drop, right? And it has a time constant. It doesn't matter whether you have a pixel, a small pixel for your iPhone, or a big pixel for your old style calculator from the 70s, right? It has the same time constant.
So
more like a limit, right?
Sorry?
It's more like a limit.
No, it's not a limit. If I have any material as a capacitance,
Yeah.
right? And somehow, as Nicholas was pointing it out, if I polarize it, right? This is polarized, right? A minus charge is here, plus charge is here. Because this thing is conductive, right? Eventually the plus charges and the minus charges will cancel out. How long does it take for that to happen? Right? It's given by this RC time constant. So this is actually a nuisance, a problem for your liquid crystal display, right? So if I charge a capacitor, eventually it will drop, right? So suppose when you charge it, suddenly things becomes transmissive, right? And then as the voltage drop, then the molecule relax, right? Then things become opaque again, right? So what you have to do is you have to constantly refresh the voltage to actually charge your capacitor, to prevent the molecule from relaxing. Any question? No? This is just an example. With that, we've done with chapter 4. Okay? Question?
Can you give a brief contrast between capacitance and resistance? Like,
Oh.
what is, I mean, just
Yeah,
kinda
so
get a
capacitance is the capacity to hold charges, right? It's actually conservative, right? So if I store a charge in a capacitor, I can always get it back, right? Remember the discussion on the energy stored in the capacitance. U is equal by 1/2 U squared over C, right? So if I put charge Q on a capacitor, right, it has this much energy. And then you can get it all back. You can get it all back as a kinetic energy, as one of the homework problems are, right? A resistor is something else. A resistor is a dissipated material. So when current flows through, you get heat out, and it goes away. Right?
Mm-hmm.
So this actually is like friction. Resistor is like friction, right? In your electronics, whenever you have R, I mean, you wish that you don't have R, but R is everywhere, right? It's a resistor, and then it actually creates heat. That's why your iPhone gets hot, right? And so this actually leads to power loss. Capacitor is just it's just a concept of how things hold charges. Resistor is about how things dissipate the energy of the charges. Okay. Does that answer your question?
Yeah, I just wanted to.
And then tau, like, what other instances is it? Is that like, is it the time until, like, is it only the polarization and how long it neutralizes, or like?
Yeah, how long does it take before everything dissipates away? Right?
That's the only time it is. It
Yes.
is that time. Okay.
In this case here, in this example,
Okay.
right? I mean, tau is just a variable.
Right.
It's equal to R. What we're talking about is the RC time constant, right?
Mhm.
So I polarize a material, right? And then it dissipates away. You cannot get it back because, you know, the electrical energy that you originally stored in your configuration, right, suddenly become current, and then the current heats up your material, and then it heats up the room. Right? And it's back to dynamic second law, right? You cannot get it back.
Mhm.
Is there anything
and that time, the time it takes for that to happen is given by RC.
Okay.
Is there any way to slow down or speed it up, or? Is it
Well,
always
yeah, you
constant?
can always, well, you can change to a material I mean, if you have a material, say metallic material, that rho is small, right? That the RC time constant is small, right? And things dissipate very fast, right? Say in this case here, right? If you make the material in between from an insulator, right? Then rho is very high, right? Then the time constant becomes very large. But sometimes you have no choice for a liquid crystal, right? This is organic molecule, is the as a polar organic molecule, you have no choice. You know, I mean, there are a lot of choices, but they all have very similar range of resistivity. You cannot suddenly change that to an insulator and it doesn't work. Because this is the effect that you're trying to achieve, is relying on the fact that it's a polar molecule.
Oh, can you alter the area of the sun? Oh no, those can't.
No, but this is the thing. This is dependent. The physics here. This is moving away from the discussion of circuits right now, right? This is physics, right? That this RC time constant is independent of size and shape. That's the take home message here. It's only dependent on resistivity. But you have a lot of room to play with, because if you look at the table in the cell, right? This is the most amazing thing about material science is that if you look at the table of resistivity, on one end here, or conductivity, right? On one end you have metal, right? And then here, this is a log scale, by the way. Here you have semiconductor. Right? And then here you have insulator. Right? And say this is, for example, it's glass. Okay. SiO2. Water is somewhere over here. Right? And this can be like 17 orders of magnitude. Go to Brazil again, I don't remember. The unit of conductivity is ohm per meter. This is -1. The unit of resistivity is ohm per meter. So the unit of sigma is ohm per meter -1. And between metal to glass, you have 17 orders of magnitude, if not more. And then you have the method of superconductivity, of course, where suddenly things has no resistance.
I was a little confused on that point. Like, why is it that lead is a superconductor when cooled and copper is a straight line conductor?
Yes. That's a difficult question.
I was trying to understand what I'm reading there, but it was a little too out there.
Yes, because what happened was that required quantum mechanics to explain, but it's a diversion. We can talk about it after class, right? Clinton's question is like, why does certain metal become superconductor and certain don't? Right? And there is a reason for it. In fact, for most metal, the resistivity actually increases as you lower the temperature. Say if you take an example of a copper, right? If you look at the resistivity of copper, as you drop the temperature, the resistivity actually, as you drop the temperature, you would think that the resistivity, right?
Well, I mean, it says that once you get into like 7.3 Kelvin, it just stays the same. Whereas lead, it goes to superconductivity.
Correct.
Or sorry, it was after 20 Kelvin.
It's all depending on the transition
Yeah.
temperature. But for
Otherwise,
most
the
metal-
conductivity goes down when you heat copper.
Yes, for most metal, when you heat it up, the resistivity increases. Yeah. Which is, sort of non-intuitive, right? You would think if you heat things up, right, things move a lot around more, then you have higher conductivity, right? When you lower the temperature, suddenly everything is frozen, then charges cannot move, then the conductivity goes to zero. Right? But it turns out for metal is actually the other way around. Right? For most metal, right? You heat it up, the conductivity drops. But certain things, when you lower the temperature enough, they superconduct. Right? So a lot of metal superconduct, a lot of material, neodymium, lead, but there's quite a few material that superconduct because of the temperature. Of course, it's a huge field. I don't know if you guys were at the H7B Lecture on Friday. How many of you were at the H7B Lecture on Friday? Right? Talks about the history of superconductivity, old and new metallic material, where things can be understood in the old classical way, all the way to the newest material that nobody understands yet. It's a very interesting field to enter. Basically, you have superconductivity, the high temperature one all the way when I first entered, when I was your age basically, entering college, high temperature superconductivity was discovered 3 or 4 years before, right? And here we are 20-something years later, right? Still not understood, still not understood. And then if you get the lecture, apparently now there are new material, or it just came out from China, that's based on ferrite arsenic. And it turns out they're all superconductors. Nobody understands the phenomenon. It's an interesting field to enter because I'm interested in studying. We don't have much time now. Any question? But,
Is resistivity of a material specific to a material always constant, regardless if there's no external factors like temperature change or anything?
No, different material have different property.
Yeah.
Yes.
So the resistivity is always constant within that material?
Within that material, all depending on temperature.
Yeah. If there was no external factors.
Yes. If at a constant temperature, then the resistivity is constant for whatever that material is, right?
Yeah.
And a lot of the calculation, if you just study solid state theory or condensed matter theory, is calculating, well, that piece of material, what is the conductivity, what is the resistivity, right? Can you predict that? Can you calculate that?
Yeah.
And can you see the dependence as a function of temperature, right?
Mm-hmm.
It turns out to understand why conductivity actually decreases as temperature increases, actually that's easy enough. You can understand it within the standard quantum mechanics. What's hard is to understand superconductivity. Then you have to go through a different kind of quantum mechanics.
So if you have like an infinite of something, some material, everywhere it would be the same, the resistivity?
Oh, well, if the purity, yes, say,
In
a lot of things become alloy. A lot of alloys superconduct, right? So the resistivity or the conductivity, a lot of time depends on the impurity. So if I have doping, right, things can change its resistance. In the case of superconductivity, we have a HOMO problem, right? The p-n junction. A semiconductor has somewhere in the mid-range as far as conductivity is concerned. It's not metal, it's not insulated, it's halfway in between on a log scale, right? You can change its conductivity, right, by actually doping it, by giving it impurity. Right? That's why you have a p-type and an n-type semiconductor, which is the example that we have here in the problem that we saw.
So the whole example they gave, where they said if you took out an electron, you also have a positive mobile charge, a mobile positive charge, that would be a hole. It would essentially move as though it had the mass of an electron.
It has a mass of similar to the mass of an electron.
Yes,
not exactly
though,
the same,
but similar to, and it would move that quickly. Is that the same in N and P doped semiconductors? Or is it, because like when you have an N doped negative conductor, your mobile charge is negative,
and then you have a P-dope, then you have the hole.
Okay. So if it's the negative one, then you've got an electron.
No, but what happened is that it's actually very complicated. It's a very good question. So in an N-type semiconductor, the carrier is an electron. Right? So it's a mass. And the mass here is not the mass, it's not the same as the mass of electron. It's not 9.1 times 10 to minus 31. Right? It's actually something else. And don't ask me why for now, right? So if somehow within the N-type, I can also remove an electron. If I remove an electron, right, then this is complicated. When I remove an electron, then I have a hole, right? And that hole has a certain mass too, right, for an N-type, right? And then you have a P-type, right, where the carrier is actually the hole. Right? It has a certain mass, and you remove the hole, you get the electron, right? It has another mass, and they're not necessarily the same because they're different material. One of them is p-type, and the other one is n-type.
So why would somebody choose to use n-type over p-type?
Oh, but it's necessary if you want to form a diode.
Oh,
A lot of
so
time
charge
in
only
the
goes
design,
one way.
yes. So the current can only go one way, right? For
That's-
electronics, often in math, we want current to only flow one way, right? You want to introduce a non-linear element to your circuit, otherwise everything is magnetic, right?
Right, so you're focused.
Yes. So you want to make sure that things only flow one way, then you have to have a diode. And a diode you can construct from a semiconductor. It's actually P and N type to semiconductor. And this is the homework problem that you have. Yeah.
So it forces current to flow only in one
Only
direction.
one direction.
Because
That's
there's like the change in N and P right there.
Yes, because of that diffusion region.
Yeah.
We can talk more about it. But I think if you go to like in electrical engineering classes, they talk a lot more about that. Because if you take a class in physics of devices, right, that's the first thing you know. But we won't go in depth into the discussion of that. But you're right. The reason that we have these two types